Well, if
Perfect. So today, Louise will present as an update her work in warm interglacial TiPES progress and planning for the next phase of PMIP. So Louise, the floor is yours.
Thank you, and thanks for the invite for this. So so I thought what I'd do is mostly give you an update in terms of what we've achieved, which is mostly focused on interglacials within the context of sort of PMIP type work, the Paleomodeling Intercomparison project. And then also a little look forward about what's planned for the next years and where we're at in terms of thinking about PMIP planning for the next years. And I have run out of time to put everyone's name on this, so I have to say this is trying to make a summary or a review partly of work which has been carried out by a lot of people, mostly funded under TiPES, which has been a fantastic project to be involved with. Particularly, I would highlight Irina, Alison, Rahul at BAS, who've all worked on this, and also as well Rachel Diamond. Okay, but I thought in terms of how we come into this is a very big picture for on Zoom. I thought I'd just sort of say partly why, or some of the background as to why I find thinking about past climate and particularly past warm periods so interesting. So working at the British Antarctic Survey, we have a constant focus on what's going on in Antarctica and around Antarctica. What we do know from lots of ongoing observations is that Antarctica is changing. Bits are thinning, particularly we're losing ice in parts of West Antarctica, Pine Island Glacier and Thwaites. But what we don't really know well from the current observations, mainly because we only have good observations from when the satellite era started in about 1979, we don't really know what the long-term pattern of ice loss and therefore what will happen to global sea level as a result of Antarctic changes over a long time. So when we look at plots like this, then you can see that by 2300, there's really a lot of uncertainty associated with the potential sea level rise. And actually in the AR6, I haven't included the AR6 picture for this, we also have a really, really high line above this, which is a storyline, sort of high sea level rise storyline version of this. So under that, even by 2100, at least in the worst case scenario, we could be looking at substantially more than 1 meter of sea level rise. But it's really the uncertainties that are the biggest problem for this. We're pretty sure that things are happening in Antarctica, but we don't really know where they will happen and over what timescales. And I'm afraid I couldn't resist putting in a couple of plots just to say like what's sort of happening and why what part of our motivation for why we're so concerned now. So after sea ice not doing very much and the Southern Ocean not seeming to do so much around Antarctica up till about 2016, things have really seemed to be happening there now. So in 2022, we had a new sea ice minima. And shortly after that, we had this massive warming event across Antarctica, particularly across East Antarctica, this atmospheric river event, which by most measurements is the most extreme warming anywhere on Earth. It's so far outside the envelope, like you kind of think it's almost a mistake. So, I mean, it's not absolutely directly tied to the sea ice loss and such like, but it certainly suggests that extremes are a thing we need to be thinking about. And then this year, things have got much more concerning. So that's what it looked like back in March time. We've had the lowest sea ice extent ever. Well, I was just trying to download as we were starting this, was a version of this plot. So this shows what the 2022 in blue, what the sea ice extent around Antarctica is. And whilst you can see 2022, sorry, in green was low, 2023 is miles outside the envelope and really not what we're expecting. So the maximum sea ice also occurred early, about the 10th of September, and has actually not increased since that time. So it seems to going back down again. So that's why it's in the news really a lot at the moment. Now, that's obviously not the same as the ice sheets. So that's not directly going to cause sea level rise. But if there's really big changes in the Southern Ocean and the sea ice, that clearly has potential consequences for what's going to happen to the Antarctic ice sheet, plus all the direct consequences on the ecosystems and potentially on the carbon storage associated with the Southern Ocean. Okay, so for paleo, for past temperatures, past climates, this is still a figure that I find useful to show just because it's so nice and simple. So this shows what we think was the sea level rise, so the loss from the Antarctic and also the Greenland ice sheets associated with past warm periods. So for the last interglacial, which is usually said to be between about 125 and 130,000 years ago, also called MIS5E, then the global warming associated with that was only about, probably actually about 0.7 to 0.8 of degree. But whilst there's quite a lot of uncertainty associated with the sea level estimates, it could be that there was 6 to 9 meters of sea level rise relative to today. So we would really like to know where that came from and why. What is the association between climate, past warm climates, and sea level rise? This is a paper that was published in 2020 by Peter Clark, and what they did was to run ice sheet model simulations for the last interglacial. You can see the plot. I don't know if you can see my cursor actually. Can this cursor be seen here if I'm waving it around at the bottom? I can't actually see anyone either to know whether that's true. Whether anyone can see it or not.
Yes, we can see it.
You can see it. Okay,
yeah.
Thanks, Kiara. Okay, so they ran basically simulations from 140,000 years ago through to about 115,000 years ago. And this shows above some of the pictures of the ice sheet shapes associated with that. One of the things that they also attempted to do in this study was to line up what they were getting in terms of the relative sea level curves here on the right with what you see in the far field, so sea level markers from Bahamas, Western Australia, Mallorca, and the Seychelles. But the thing that I find interesting is that you obviously need those ice sheet models need to be driven by climate models output, or else they need to be fully interactive. So we need to basically have a really good understanding of what the polar changes are to be able to drive these ice sheet models. And here what they're suggesting is that the West Antarctic ice sheet did collapse at this time, that this gives you a reasonably good match with the far field evidence. And that, of course, is then giving you this really quite large rise in sea level of probably more than 5 meters, although it depends precisely where you are in the globe as to precisely what that number is. So that's something on the motivation for why I'm particularly keen on paleoclimate and particularly thinking about what the polar regions were doing during past warm climates. So I thought I'd just say something quickly about kind of PMIP itself and how that works to inform our understanding of past climate. So PMIP itself is kind of a sub-MIP of CMIP, or at least it has been for the last couple of cycles. So we're now coming up to CMIP 7, the coupled model into comparison 7 period. Our project. So PMIP will again be a part of that. Our numbering is not quite right. So we've been a bit out of cycle. So we might be PMIP 5 for PMIP 7. Well, I'm still not CMIP 7, but I'm not absolutely sure about that. But the key thing is that PMIP has been in operation for 30 years now. And what it essentially does is, I would argue mostly it creates standard model protocols. It does more than that as well too. So for the last interglacial, we try and keep things reasonably simple where we can for the modelling groups. So all the modelling groups are expected to run all the DEC, CMIP simulations, plus all the future projection ones. But by giving modelling protocols for past periods, it means you can absolutely directly compare the results from these models for past climate to what we're getting in terms of their future projections, and thereby tie it into the science that is most relevant for the IPCC. So our protocols look something like this. So on the left, they're the pre-industrial, and basically on the right here for the last interglacial, the group chose 127,000 years ago as a single time slice, under PMIP 4 for CMIP 6. And in essence, there's actually not a lot of difference between the last interglacial PMIP protocol and the pre-industrial. The main difference is the orbital parameters. So the greenhouse gases are really not terribly different between the pre-industrial and at least the last interglacial, and that's true for some other warm interglacials too. 10 parts per million in CO2 is not a huge difference, but this orbital forcing is a big change. So this shows against latitude what the top of the atmosphere shortwave radiation flux anomaly is compared for the last interglacial compared with the pre-industrial. What you're looking at is an anomaly of up to 70, it's just over 70 actually, watts per square meter in spring and early summer in the high northern latitudes in the Arctic, and a similar anomaly for Antarctica as well, slightly smaller, and the distribution is slightly different. So that's what's really generating most of the signals that we're seeing in climate, or at least the direct signals that we're seeing. So having laid out that protocol, then PMIP attempts to persuade as many modelling groups as possible, although I have to say many modelling groups are actually really very keen on setting the models up for these paleo simulations. So for the last cycle, we had the models there listed on the right, who ran this last interglacial simulation, all using that exact same standard protocol. So you could say there's about 16 simulations, but given some models are really from the same family, it's hard to say how many, if you like, independent simulations there are, but I would say it's kind of more like 11 or 12-ish. But that's still pretty good. It's not as many as run the DEC or the projection runs, but it still gives us a lot of model output to work with, which helps with a lot of different types of paleo questions. So some of those models have then been used under TiPES, and I'll show you some of our progress that we've made in terms of Arctic climate during past warm interglacials, and really just focusing here on the last interglacial, and a little bit about consequences and importance for the Greenland ice sheet. So for the last interglacial, we know from ice cores that at least the water isotope signature was a lot less depleted for quite a prolonged period, actually. Between about 126 and 120,000 years ago, it looks like, mainly from the Neem core, but from other the ice at the bottom of other cores as well, which has been dated, it looks like there was a longer period where possibly not so much happened to the isotopes in Greenland, but certainly relative to the present day and the pre-industrial, it was a lot less isotopically depleted, and that has been associated with the warming, or summertime warming, of up to about 7 to 8 degrees. Though it's not always trivial to interpret these water isotope measurements directly as temperature. Regardless, for 6,000 or 7,000 years ago, it was a lot warmer in the Arctic. We know that from the ice cores. We also know from measurements beyond Greenland, which involve a variety of core material, terrestrial, crystalline, marine cores, that there was strong summertime warming during the last interglacial. It's not absolutely clear, to be honest, that absolutely all of these proxies are from 127,000 years ago, but they're effectively lined up as being peak warmth proxies. So if we assume that there was a plateau for some time period, then we can assume that we're kind of sampling here the warm part of the last interglacial for the Arctic. So we had these, most of these observations showing a very warm Arctic for actually quite a long time. Which showed that these core mean values gave you a warming of about 4.5 degrees warming than pre-industrial. But for quite a long time, we really didn't know why. And that was partly because none of the models actually simulated this warmth until, I would say, possibly slightly serendipitously, at the start of TiPES project, we found that one model did actually simulate this. So for this plot here, I'm showing the modeled summertime temperature anomaly between the pre-industrial and last interglacial, and then the proxy temperatures from the data set. So obviously, given that when we set our model up with that standard PMIP for last interglacial setup, so it was a standard PMIP run, so really just forced by this strong insolation anomaly in springtime, we wanted to know why we got the model to be so warm, and warm enough that for the first time it seemed that we actually had a model that matched the observations. And what we found was that the model basically had no sea ice left after it spin up. So if you look here for the pre-industrial here, this plot is showing the sea ice area. So for the pre-industrial, we've got a reasonably accurate simulation of the Arctic sea ice extent. But as soon as you implement the last interglacial orbital and greenhouse gas conditions, you have a massive drop-off of the sea ice. And by about 15, 20 years, you have continuously sea ice-free summers. Sea ice-free is usually defined as under 1 million square kilometers of sea ice. We have to have a threshold for it because there's always little bits of remnant ice around, stuck around the edges. So it needs a threshold value, and that's why the 1 million square kilometer value is used. So in essence, what we found was happening, this is in various papers now that we've written up, is that this radiative forcing, this really strong radiative forcing here, led to an earlier onset of melt on top of the sea ice, so snow melting and turning to water. And then because the ponds have a higher albedo, then you have a feedback, and then you basically have a higher sea ice melt rate, and then as you get a darker surface on top of the sea ice, then you can get a complete loss of the sea ice. So the red line shows the melt pond area for the last interglacial simulation. You see it goes up much earlier than it does for the blue line for the pre-industrial simulation, peaks a bit higher. And the reason it then goes down is simply just because there's no sea ice left. So you can't have melt ponds because there's no sea ice for the melt ponds to be on. So that results in a complete loss, or effectively a complete loss of sea ice for this model. Because we then have the output from all the other models which have run this exactly the same simulation through PMIP, then we have the ability to look and see whether our model is doing the same or not as the other models. And what we find is our model is anomalous. It's not entirely anomalous in the sense that there's at least 2 other models, I would say arguably 3, which also have really very little sea ice, and every single model loses a huge amount of sea ice. So all the models are in agreement, all the simulations are in agreement that you have a really big reduction in sea ice, but only 3 have at least an occasionally sea ice free Arctic. Those 3 are CSM2 and also I think it's NOR. Did I circle them? Yeah, it's the NESM3 model. So you can possibly see that if you look at the plot there, which is showing a cumulative PDF. So you can see for which years or which summers it's sea ice free. Of those, NESM3 model does some slightly odd things with sea ice, so we're a little bit less sure about how to interpret some of that, and it has a less good representation of present day sea ice. But for the 2 which have a sea ice free Arctic, CSM and HADGEM3, the interesting thing about that, when we first looked at that, is these are the 2 that have exactly the same sea ice scheme. It's a size 5.1 sea ice scheme. And the critical thing for that is that it has explicit melt ponds in it. So rather than just an implicit albedo scheme. So the reason we think these 2 are doing much better in terms of their temperature, capturing the temperature change in the Arctic, and losing more sea ice, these 2 things are effectively in some sense the same thing, is because they really do represent these things, melt ponds, better than some of the other models. And when we do some basic tests with the against temperature data, we do see that we get a much better match. So Rachel Diamond has gone on from that and also looked even more carefully, because we still, whenever you do coupled model work, you're always slightly questioning yourself as to whether you've fully isolated why you're getting the results you are. So to try and make absolutely sure that it was down to this explicit melt pond scheme, Rachel has run another set of simulations, both for the last interglacial, but also for the a warm near future as well too, plus the pre-industrial. So she's run that with 3 schemes: the explicit melt pond scheme, and the sea ice model is the orange results, and then an implicit scheme, which is generally thought to be pretty much equivalent to the explicit scheme, is in green. So people generally assume that you get pretty much the same results for that. And then a 3rd version where the melt ponds, we attempt to kind of turn them off. So what you find, and what I find interesting for this, is for kind of most of the historical period and for the pre-industrial, it does not really matter if you run with an explicit or an implicit melt pond scheme. That can be seen because the orange and the green lines are really quite similar, especially for the pre-industrial. But when you have a warm climate, such as the last interglacial, or you go into the future, what we're finding is it really does matter, and they do give you really different results for the sea ice, and therefore also for Arctic warming or Arctic amplification. So that's all down to these positive feedbacks, which really kick in when you have thin ice and warm climates. Yeah, I just added this in as well because I like this paper. This is not my work at all. But this then goes and takes effectively, well, it's actually a fully coupled run, but uses a version of the CSM model to then try and go ahead and drive ice sheet change in association with this warm Arctic. So I wouldn't say the setup for this is absolutely perfect, but it is really nice that what they do attempt to do is look at meltwater feedbacks and then also vegetation feedbacks as they run with a warm Arctic over this last interglacial period. You can see the times at the top and what's happening to their ice sheet model as you go through time. So yeah, basically you need to know, and I don't think their model's quite right in terms of its sea ice in this version, but you need to know really quite well what your climate is of the Arctic throughout this period to know if the forcings on the ice sheet model is right or not. But it's a really nice paper, this. I don't know how long I'm going on for here. Okay, we'll go through this usually quickly. But I would say during TiPES, this was just an attempt to summarize like what we've learned. And I would say really we've learned a lot. Maybe that comes across from all the words on this side. So I think at the start, we really didn't know why the Arctic was warm. It was postulated to be down to a lack of dynamic vegetation and why models didn't capture the warming that we saw in observations. And throughout the period of TiPES, the sorts of studies that I've already gone through now show that actually it is sufficient to have improved sea ice model rather than a vegetation model. And we've learned really a lot about melt point physics, and also actually therefore something about how reliable the models are for future projections, which I think was not well understood before this. So it's nice that some paleo work is therefore kind of fed into the future, the understanding of future Arctic changes. In future, and hopefully under PMIP 5, it would be really nice to also go ahead and better test the impact of dynamic vegetations as well as improved sea ice models, now that more models have the ability to simulate dynamic vegetation. But as a kind of short form of that, if anyone just likes Arctic in the last interglacial, is that we do think that actually the Arctic warming was actually about 3.7 degrees, and we think we now know that there was roughly 1.3 million kilometers of summertime Arctic sea ice left. So that basically means it's all right on the border between sea ice free and sea ice present. So that we think that there was a mixture of sea ice free and sea ice present summers. And actually there's just been a paper which has been published in the Nature journals, which uses entirely different data and really, really nicely suggests that we were actually right in everything that we were doing on this. So that's really lovely to see. Arctic sea ice change, notwithstanding the fact that I think we need to do more on dynamic vegetation, seems to be key to understanding the climate of the region. And I think that's something that's only been realized during the period of TiPES. But we do need to know, I think, even better to do accurate ice sheet and sea level modeling what was going on in the Arctic. Okay. I'll talk a little bit less about some work that we've also done on this sort of thing for Antarctica as well. So I would say, hopefully this doesn't take quite so long. But it's going to come back a bit to sea ice again. So before TiPES started, Max Holloway and I wrote up a few different papers between 2016 and 18, and he was a great PhD student who worked at BAS with me. And what we found doing water isotope modeling that time was that as well as the Arctic being warm, the ice core water isotope signatures suggest that around Antarctica, sometime in the last interglacial, to be able to match the ice core results, we probably did need quite a big reduction in sea ice, maybe of 50 to 60% of the wintertime sea ice area, partly because there's not much sea ice in the summertime. So for TiPES, having noted that we really needed additional independent data to say whether this interpretation, which is based on using on the interpretation of water isotopes with lots of water isotope enabled climate model runs, whether this was correct or not. The reason for that is shown sort of in these plots, especially B and C. So A shows that if you get rid of loads of sea ice, you have a good match between your simulated water isotopes and what you see in the ice cores. That's the match between the sort of orange ice cores and the mostly orange simulated output from our water isotope enabled model. But we effectively were then suggesting that the sea ice edge in the winter time for the last interglacial peak warmth had gone from where it was in B back to C. But most marine cores, which can be used to say whether you were close to the sea ice edge or not, had been drilled close to the current seasonal sea ice edge. So they're basically too far away from the sea ice edge to TiPES whether we were correct or not for this. So during TiPES. There was work done actually by other people as well. I think under TIPEX as well, I found recently. But work done by us, which Matthew Chadwick, who was working with me on this, found another 8 cores which were closer in to Antarctica, where he thought he could date, he and Claire Allen thought they could date the last interglacial. So he basically spent 3 years picking assemblages from these cores to try and test whether or not we were right or not on this. And the outcome from that, which is a TiPES publication, this one in 2023, says that probably there was less sea ice. I'm not sure these are actually the very best figures to show this. And they basically support that there was a warming around of the Southern Ocean. But there is quite a lot of variability that we find between the cores. So this suggests that, frankly, some of this work is quite hard to do. And possibly also there's localized effects that we maybe still don't absolutely fully understand, which are affecting the marine core data we have. But anyway, we effectively slightly refined what we think is the peak Southern Ocean warming, at least south of the Antarctic polar front. And Matthew's suggesting that that should be about 1.5 degrees warmer than the pre-industrial. And that is super useful for people trying to drive their sea ice models, and their ice sheet models too. The key thing for PMIP, however, is that unlike the Arctic, where at least some of the models do quite a good job, for Antarctica, there is no match between the observations of Southern Ocean sea surface temperature peak and sea ice change and what we see in the models. This has been done by, well, actually, a few people have worked on this. Matthew again, and also Qinggang Gao, who's a deep ice student working with me and also on TiPES work too. So he's showing here, this is not published actually yet, but he's showing that there's really no match when you take all the data syntheses that are out there and Matthew's new data sets. You do not get anything like the warming that we see in the observations. So in the PMIP-3 and the PMIP-4 last interglacial experiments for the Southern Ocean, there's a huge amount of spread. No, I didn't highlight this, but you can see that here, if maybe with my cursor, in the Southern Ocean part, and the fact that all the models show really different patterns of warming relative to the pre-industrial, and a lot actually show cooling as well. And what he's showing here with the plot above is that there's no match and there's no improvement between PMIP-3 and PMIP-4 models. However, I have to say I am not at all disappointed in that, because what we have published papers and we have looked at this before, and we believe, we're really quite sure now actually, that the reason that we do not have a match is because the Southern Ocean and Antarctica is responding to meltwater that goes into the Northern Hemisphere during termination 2. So just before the last interglacial peak, we had the loss of the big ice sheets in the Northern Hemisphere. So if you add that meltwater, or a version of that meltwater, to the Northern Hemisphere, then this is showing a simulation which is 1,600 years long, well, a couple of simulations. One, the orange simulation results there, where we're adding roughly 0.25 spheredrops of meltwater to the North Atlantic. So effectively a standard hosing of a last interglacial experiment. And if you do that, then you do warm up the Southern Ocean. I'm not sure we've fully got it warm enough after 1,600 years. We're running these experiments now a bit longer, but we certainly have a much better match, and we have quite a large loss of sea ice associated with that too. So possibly those results are still not quite warm enough, but you can see on the right that the results for no meltwater are the same as all the other PMIP-3 and PMIP-4 results. There's really almost no warming. There's basically a tiny amount of sea ice loss associated with insulation forcing, but it's only tiny, mostly because there's no summer sea ice around Antarctica to lose anyway. But the by 1600 years of this meltwater forcing in the northern hemisphere because of the bipolar seesaw and standard hosing results, which are reasonably well understood already, actually, you have this warming. So for people who are interested in ice sheet changes, I keep trying to push them towards using these sorts of simulations rather than standard PMIP3 and PMIP4 last interglacial ones. Yeah, so a shorter summary for TiPES work on this. On the Southern Ocean and Antarctica. Well, in essence, Antarctica is really, really worrying at the moment. So I think a lot of people really have a lot more focus on this now than we have in the past. Are we at a turning point in sea ice? We certainly want to know about that. So in terms of looking backwards at the last interglacial, it is interesting to know that this is a period where it looks like there was really a big sea ice loss, probably the last time there was a big sea ice loss. So it's a useful period to test our models about. And I think our results so far mostly confirm what we actually already knew by about 2018, which is the Southern Ocean was a lot warmer. Probably there was a big sea ice loss in association with that. We could still do with more evidence for that if we could find it. And that if you do want to do ice sheet modelling or other types of simulations for this period, then it probably really is necessary to take account of the termination to Northern Hemisphere meltwater. So it was often called the Heinrich 11 event. So if that is done, and that is something that we'll be looking to include as probably a tier 2 experiment for PMIP5, therefore. Okay. So the last thing I wanted to spend the last over time, we've got another 5 minutes or so, I maybe won't go through all of this, is just to say what are the plans for the next phase of the paleo modelling into comparison project, again with a focus with my obsession on warm periods and also on polar regions mostly. So for the past 10 years or so, the lead on the interglacial side was Betty Otto-Bleisner. So she's done, in conjunction with Dan Lunt, a really good job of shepherding PMIP4 and PMIP3 in terms of the last interglacials. But the Syrian group kindly then asked Christian, Stefanik, and myself to take over this. So at the moment we're putting together both some nice web pages, which is mostly Christian's work, I have to say, and we're putting together some of the groups of people we need in terms of the observationalists and the modelers to move forward and define protocols for PMIP5 and how we go about that. So we have a very complicated looking schematic. We are kind of at the moment just in this bit in terms of the PMIP5 timeline, but what we mainly need to be keeping an eye on is really like the timelines for CMIP6 model development, when DEC simulations and core simulations will be running, what will be the deadlines for papers which get into AR7 as well too. So we need to think about that. But at the moment we're basically discussing how to set up the group, what meetings we need, and preliminary discussions on protocols and choice of periods. So I think we put this figure on our website if anyone wants to look at it. And the other thing that we've done so far is to send round a community survey. So it's nice that of the 25 people who'd responded by the beginning of this month, so I don't actually know if we've got more now or not, we have either 14 or 17 models. And I'm not entirely sure about this, but at least we seem to have at least as many, if not more, modelling groups who would like to be a part of PMIP5 and would like to do interglacial experiments. And in a way, this, I think, makes a lot of sense because honestly, running the interglacial experiments for modelers is not so difficult. Running experiments with really significantly different ice sheets and other land sea masking changes is difficult, but some of the interglacials are less so. So we have people involved from well, across the world, and pleasingly also seem to have quite a lot of people on the data side too. So there's lots of lots of different questions that people have said interest them for what they'd like PMIP to help with. Amongst them, things like how warm were past interglacials, how much, what rate did the ice sheets retreat at, what was the influence of changes in ice sheets and sea ice on global and regional climate, how much sea ice was left, did sea ice changes influence ocean conditions and regional climate. We are discussing quite a lot different time periods at the moment. So I'm not sure what the best one. Maybe this is actually the easiest thing to look at for this, and maybe we'll actually stop here to give time for discussion. That's probably better. So MIS1 is a pre-industrial effectively. So this shows what the top of the atmosphere insolation anomaly at 65 degrees is. Actually, I have to say Christian made this. I am slightly confused as to how he's lined this up and what he's put for this. 35. Oh yeah, because I was thinking it should be 0. Okay, it's 0 at the end of the line here because this is a sort of the pre-industrial. So the top of the atmosphere anomaly at 0 is in the pre-industrial, or at least the last millennium, is more or less 0, which is what we'd expect. But then what he's done is lined up other interglacial periods, because we're often thinking a lot about what the impact of insulation forcing is, although of course what's happening in terms of melt of the ice sheets is really important too. It might be that it's a good idea to try and select periods which are a bit different from each other. I think it's very likely that we'll keep a simulation for the last interglacial, or MIS5E. That's the orange line shown here. He's lined them all up here with this sort of peak or second peak. So you can see this is one of the most intense periods in terms of the insolation anomalies. But another one that we think we might try and have a protocol for is this much lower one. So MIS11 is quite an interesting interglacial. It was about 420,000 years ago, but it was a really long interglacial where probably sea level was quite a lot higher than present day. The insolation forcing just kind of stayed moderately high for a really long time. So that would enable us to look at things like the impact of duration versus intensity. But I am also slightly tempted, I'm not sure how many other people are, by MIS31, just because it's massive. Like, it's such an intense insolation peak. So I don't know, have I got... Yeah, so say for this, you can see that MIS11 is actually quite similar to the mid-Holocene period in terms of its insolation forcing. And we have lots of stuff about why we might be interested in it. But MIS31, whilst it's 1 million years ago, so we don't struggle a lot more for having good data sets, it is incredibly intense. It's considerably more intense in the north and the south compared with the last interglacial shown there above. Yeah, I shall go back to this rather than talk more about that, and I'll leave that there. So I will stop talking there, and I hope that covered at least some of the things that people may be expected on this. And I would just say I'm quite excited about, we're going to have another PMIP period, another PMIP group who's going to work on interglacial. So if it's something that also does interest you, any of this, then please do get in touch with me or Christian. We like people to join the group in terms of contributing their many different types of expertise in it. So I'll stop there. Thank you very much for listening. And if there's any questions, then I'm very happy to attempt to answer them.